Welcome to Session 4 on why and how to ground electrical systems. Grounding is a very confusing, misunderstood topic when it comes to electrical systems, and I hope I don't add to that confusion for you. Hopefully I can help straighten out some ideas. But I want you to be careful, to be thinking about the concepts that I present in this session, see if they make good common sense to you, and then if they do, maybe you want to adopt some of these ideas. The main thing I'll be trying to convince you of in Session 4 is returning signals to their sources has nothing to do with grounding of signals. Returning signals and grounding signals are two completely separate ideas. There are quite a few misconceptions regarding grounding. Probably the number one misconception is thinking that ground is actually the current return path. Thinking that ground is the current return path. This is not a little bit wrong. This is 100% wrong. Completely wrong. The idea that we need a good ground, that we need to be able to sink noise currents into the earth with a good ground, that's also quite a bit misleading. There are times, yes, when we want lightning currents and other currents to be able to find a good low impedance path to earth. But in general, the idea that by getting a better connection to earth that we're somehow going to dramatically reduce our noise troubles, I don't think that works that way very often. A lot of times people do not want to connect their electrical systems to building steel because they think of building steel as a source of noise. They instead want an alternative, a different low noise ground. Usually accomplishing that results in serious safety problems and not acceptable. What is electrical ground? First we'll talk about that topic, what is ground, and then we'll discuss why we would connect something to ground. Electrical ground is going to normally be a good conductor. Not always a metal, but usually something metal. I don't like using the word good conductor, but if I took the time to try to explain in detail just how good a conductor we're talking about, I think we'd lose track of the whole concept. So a good conductor, usually something metal, but the earth would be large, not as good a conductor as metal, but it would count in some instances as well. So the ground structure is going to be a good conductor. What else? The ground structure typically is going to be a large surface area, large relative to the system we're dealing with. If we've got a circuit board the size of our hand, then we're talking about a surface somewhat larger than the size of our board. The ground structure also needs to be electrically close to the system. If it's several thousand feet away, then it's not close enough to interact. But probably we could measure close in terms of a wavelength, I suppose, but I don't think we'll need to do that. I think we'll understand that a metal structure within a few feet of an electronic system possibly is able to interact with it electrically, and if it's a few thousand feet away, it's probably not able to interact. So the idea of what's sufficiently close, I believe, will be easy enough to determine also. But a key thing about a ground structure, I believe, is the ground structure is not part of the signal current path. This is the item number 4, that most electronics people would disagree with me on this. It seems like to most electronics people, the ground structure is considered to be part of the signal path. And that's where I make a serious distinction. I do not consider returning currents to their sources as having anything to do with the grounding of currents. So this is what electrical ground is. Good conductor with a large surface area within a few feet of the electronics, but this metal, usually it's metal that we are talking about, is not part of the signal path. Here's an example. Let's say we're talking about electronics on a metal frame commercial airliner. So this rectangular box is my representation of an airplane. That's about as good as my artistry is. On commercial airliners, there are two classes of signals. There are non-critical and critical. Non-critical to safe flight and those critical to safe flight. The critical signals will typically use the metal skin of the airplane as the current return path. And of course, the simple reason for that is to reduce the weight that would be associated with other added conductors. And if, when lightning strikes the airplane in flight, if these signals are disrupted, it's not critical to the safe flight of the system. For the critical signals, the typical signals they're run on a twisted pair, over on one conductor, back on another conductor in the twisted pair. For this type of signal, how should we view the metal frame of the airplane? It's a good conductor. It's a large surface area. It's only a few inches away from the wiring, but it's not part of the signal path. So I would say for this current, the metal airframe is part of the grounding structure. Whereas for the other signal, the metal airframe had a higher function. It was not part of the grounding system. It was part of the actual signal path, what I would call the signal return path. So I think we have to be very clear in looking at any given situation. Is the metal that we are discussing, is it part of the signal carrying path, or is it not part of the signal carrying path? If it's not part of the signal path, then it might be part of the grounding system. In fact, it probably is, and we should be thinking of it in that manner. But make a clear distinction between whether the metal is intended to carry the signal or not intended to carry the signal. The example I just did for the aircraft, you can see that the same piece of metal can serve multiple functions. Same piece of metal could be the return path for one signal and yet part of the grounding system for another signal. What are some possible electrical ground structures? Well, building metal is a good example. It could be part of the grounding system. In fact, it's more likely to be part of the grounding system than part of the signal path. At least we hope it's that way. Metal vehicle frame could be part of the grounding system. It could also be part of the signal path. It depends. An equipment chassis. This is a tough one. This is one we've got to be careful about. Do we want our signal currents to flow on the metal equipment chassis, or do we not want that to happen? Do we want the equipment chassis part of the signal path, or do we prefer to have it as part of the grounding system? The earth, of course, is an example of something that's probably not normally intended to be part of the signal path. However, here might be one reason why we have this trouble with confusing ground with return. Years ago, in the early days of power distribution, they sent out one conductor to carry the AC power current out to the load and used the earth as the return path for the power current. In that situation, the literal earth was part of the signal path. And I think even in some of the early days of telegraphy, they used one wire. Of course, they had a lot of noise troubles using the earth return, so they pretty quickly shifted over to a two-conductor wiring path for telegraphy signals. But maybe it was the early days of using the earth as the power return that we got into the idea that ground somehow should be associated with the return path. That's no longer true at all today. The power people, the safety people, do not think of the earth normally as part of the return path. Well, except in certain situations, maybe they do. Let's now talk a little bit about the reasons for grounding. Obviously, there's safety, electrical safety, and the purpose here is to reduce the voltage differences that might exist between exposed conducting surfaces that could likely become energized. And of course, the way to do that is to bond those conductors together, short out the voltage difference. I think we all have a pretty good understanding of the need for safety grounding. We probably don't all understand adequately well the requirements. We're not as familiar with the National Electric Code maybe as we should be, but at least we know that there's significant amount of grounding associated with some safety requirements. But what would be a second reason for grounding other than safety? A lot of times when I ask people, they say, well, other than safety, you need to return currents back to their sources. No, I don't think that's it. In fact, I know that's not it. Other people say there's safety grounding and there's noise reduction. Now, grounding to reduce noise, well, there's some element of truth in that. But see, if I said the two reasons for grounding were safety and noise reduction, I think that would incorrectly give you the idea that if you had a noise problem, likely then what you need is a better grounding system. And a lot of noise problems are not related to grounding troubles at all. Some are, some aren't. How do we tell the difference between them? I think we need to phrase our reasoning for grounding in a way that differentiates between those noise problems affected by grounding and those that are not. So I think really a second reason for grounding is to reduce voltage differences that might exist between signal reference points. like between the analog reference and the digital reference. The voltage difference between analog and digital references, that voltage difference can very easily lead into a noise problem. So if we can reduce that voltage difference, provide a better reference for the analog and digital circuits, that will eliminate some of our noise problems, those associated with a referencing problem, but it will not, of course, eliminate magnetic fields picked up by signal loops. That's something completely different. But I think if we phrase it this way, we'll understand the difference. There's safety grounding, which is to reduce the shock hazard voltage, and then there's signal referencing, and that reduces some of our noise problems. When it comes to safety issues, as I show here, I show two metal objects between which there might be a hazardous voltage. Well, depending upon the environment, the power level and the wiring and so forth involved, the National Electric Code will specify a certain minimum size conductor to be bonded between those two metal objects. If we do that, we will meet the code requirements. But supposing someone else comes along and adds some additional grounding connections that we had not intended. Do those additional safety grounding connections destroy the purpose that we're trying to achieve? No, they do not. They may be unnecessary, but they do not destroy the safety grounding. So I think you'll find that when it comes to safety grounding, there oftentimes are many connections, more than we really need, but that is typically okay. We're going to see with some examples in a moment that when it comes to signal referencing, very few critically located connections are usually what we require. If we have a large number, or even just one or two additional unintentional connections, those could actually destroy what we're trying to accomplish. So with safety grounding, many connections are likely to be possible, likely to be present. But with signal grounding or signal referencing, we want to be very careful to put in just a few of the correct, properly located connections. Here's a simple example of safety grounding. We have a metal equipment chassis with single-phase AC power coming in. We have line and neutral, and we have the safety ground, which we normally call it, sometimes the green wire ground. The official name, of course, is the equipment grounding conductor. The purpose of the equipment grounding conductor is to hold the external chassis at about the same voltage as the surrounding ground surface, which in this case probably is a building structure, building metal. Minimize this voltage difference. We want this voltage difference less than a few volts. Doesn't have to be exactly zero, but as close to zero as reasonable. And now here's the problem, though. We don't want this voltage minimized just under normal operating conditions. We'd like to try to hold this voltage to a low value under fault conditions. Now, probably we realize we can't do that completely. If the line conductor were to short to the chassis, and if the line conductor were of the same resistance as the equipment grounding conductor, then for a brief moment, hopefully not a moment, but for milliseconds maybe, this voltage might go up to half the line voltage until the breaker, which I didn't show back here, the breaker trips and then de-energizes the circuit. So normally we have to try to make sure that the equipment grounding conductor has a very low resistance and low inductance path so we can get a large amount of current very quickly and rapidly open up the breaker and de-energize the circuit. Most of our safety is brought about by rapid de-energizing of the circuit, and that requires high fault currents actually, better high fault currents than low fault currents. But that's safety grounding. The purpose of this conductor is to hold this chassis at near ground potential during most of the operation. What about a signal grounding example? Well, here's the classic difficult signal grounding situation where we've got an A to D converter. Now let me try to distinguish between routing of signals and grounding of signals. I'll use the blue color for routing. We have an analog signal we're going to bring into this A to D. That analog signal needs a return path back to its source. So there's a loop there of some sort which carries the analog signal current. Similarly, on the digital output side, let's say this bit line is being driven high, and at this moment we've got current coming out this line going to some place which we'll represent as a load resistor. This current, of course, needs a return path back to its source. So there's a loop here that this particular current, digital current, has to pass through. Controlling the size of that loop, minimizing the wiring inductance, and all of those issues has, in my mind, nothing to do with grounding. Where does grounding come in? Well, we'll switch over to the black pen. Let's say this point represents the analog reference. When we measure voltages on the analog side, say our signal going in is 100 millivolts. 100 millivolts on this pin relative to where? Well, we'll say it's relative to this pin, which is our sort of default analog reference. On the other side, we've got a signal coming out. Say it's a 5-volt digital signal. 5 volts relative to where? 5 volts relative to the analog reference? Maybe, but probably we mean 5 volts relative to the digital reference, which I'll show over here. So we have a point which represents analog reference and a point which represents digital reference. What would we like the voltage difference between these 2 points to be, between these 2 references? The voltage indicated here. We'd like that voltage to be approximately 0. Now in the case of safety grounding, we said less than a few volts might be adequate. In the case of signal referencing, however, it's going to have to be less than maybe a few millivolts to be adequate. So the degree of voltage reduction that we need for signal referencing is usually a lot less than what we need for safety. How do safety people reduce the voltage difference that might cause a shock hazard? They bond the 2 objects together. How are we going to reduce this voltage between the reference points? We're going to use the same approach. We're going to electrically join, with a conductor, electrically join that reference to the other reference. Now, when we make this referencing connection, how much current do we expect to flow through there under good operating conditions? Well, maybe we didn't discuss this enough previously with the safety ground. We did say that safety grounds are supposed to carry considerable current during fault conditions, or maybe lightning conditions. But under normal operating conditions, how much current should flow through a safety ground? Minimal amount of current. Not 0. 0 is not something that's possible. If you've got you say you got a power cord where you got line, neutral, and ground, 3 conductors here. There's a voltage between the line conductor and the grounded conductor. So you do expect there to be some capacitive coupling between those 2 conductors. Even with no load attached to the cable, if the power cord is energized, there will be a tiny amount of current coming back on the ground wire due to the capacitance that naturally exists in the cable. So under normal operating conditions, we don't say that the safety grounding conductor should carry no current. In fact, I think the wording that the electrical code uses is it says no objectionable current. And of course, then most people say, well, what does that mean, no objectionable current? Well, you have to look at the given situation. Look at how much load current there is and see. You can't put one number that will cover every conceivable situation. Now, in some applications, and I believe maybe this is an underwriter's laboratory requirement, but in some applications they say a single cord-connected piece of equipment should carry on the grounded conductor less than 3.5 milliamps. There they try to put a particular number onto how much current is allowable. But that's for a specific situation. That can't cover every conceivable case. But the idea is this. Safety grounding conductors carry no objectionable, sort of minimal current under normal operating conditions. But they do carry some little bit of current. Now the same is true for signal referencing or signal grounding conductors. They also carry a little bit of current, but no significant current, hopefully under normal operating conditions. So we go back to this situation right here. What if we found that as this digital current pulse was switching here, what if we found somehow a considerable amount of that current returning on what is supposed to be a non-current carrying referencing connection? What would we do about that? Well, you see, a lot of times the approach is put some impedance in here to block the ability of this current to flow. No, that's not the right approach. If we add impedance here, then this voltage that we're trying to minimize will no longer be minimized. We'll be losing the reference that we need. The idea is this: if some of this current somehow found its way over to this path where it should not be, what that means is there's a problem with the routing of this current. Why isn't this digital current staying on the intended path? Why is, say, 10% or maybe 90% of it's here, but why is 10% of it taking some other path? Well, possibly because the impedance of the desired path isn't low enough. If we lower the impedance, and that usually means inductance of the preferred path, then we can get much higher value of current here and a lot less current over here. So what I think we're saying is, in many instances, when you find an objectionable amount of current on a grounding conductor, whether it's safety or signal referencing, that doesn't mean we should necessarily add impedance to that path. We should find the path that is supposed to be effective at carrying that current, fix that path, that is, lower the impedance of the intended path, and that will reduce the current on the grounding conductor. Another typical question about signal grounding or signal referencing is, where's the best place to put the reference connection? Here we show an A to D converter that is running off of two different power supplies. Maybe we have a 12-volt supply for the analog side, maybe a 3.3 or 5-volt supply for the digital side. Should we put the reference connection near the A to D converter, or should we put it near the two power supplies? Well, we want to put it where it matters the most, where it makes the biggest difference. In this case, the two power supplies don't need to be at the same voltage. They don't need to have the same reference. It's the A to D converter that really matters in this situation. So I'm going to show a connection here. This is the preferred location, clearly the preferred location for the signal referencing connection. And we would like very little current, either digital or analog, to pass through that connection. Now notice again, to kind of distinguish with colors here, we expect the analog supply leads to carry current. We expect the digital supply leads to carry current. Those are supposed to be current-carrying conductors, but we don't expect the reference connection to carry much current. Let's assume for the moment that sitting off here to the side is a considerable amount of digital circuitry, all represented in one little box there. So let's show a pair of power supply leads going into that circuitry. Let's say that this circuit draws quite a bit of power. Let's say the total current going out is 5 amps. With the way I've designed the system so far, the only place this low-frequency current can flow is back on the intended path, right here. Now, I said low frequency. You might say, wait a minute, that's the high-speed digital circuits doing the switching, so this could be higher frequency. No, remember, we've got decoupling capacitors out here that I didn't bother to show. All the high-frequency currents are coming from a local area right near the load. The only thing coming off the power supply line is the lower frequencies. Frequencies may be in the kilohertz range. But the way I've designed it so far, the low-frequency current can only take this path. Remember what we said earlier about low-frequency currents. They will take every path available. If we give them more than one path, they will use more than one path. And generally, that's not a good idea. That's not what we want to have happening. Look at how we could mess up this situation here. Supposing we put in the one reference connection that we think is necessary at the A to D converter. Somebody else comes along and says, well, but there's no reference for the power supplies. So let's put a reference in for the power supplies. So I'll draw a lead in black, which is supposed to be non-current carrying. But look at what happens as soon as we do this. Now, instead of having 5 amps return back here, we'll probably have 3 amps returning there, and we'll have 2 amps or more going over this other path. A significant amount, amperes of low-frequency digital current, will flow across the reference, through the analog supply lead, and back again, and this will mess up everything. We can't allow this, but this will happen. The way we make sure this doesn't happen is we do not give this low-frequency current multiple paths. Give it one path back to the source. That'll keep it where we want it, and that'll keep it the problems a lot less in this situation. So we saw with safety grounding that very often people will put in multiple redundant connections. That is allowable. Maybe again it's not needed, but it's allowable. What about putting in multiple redundant sort of parallel safety or signal grounding connections, like we're showing with the A to D converter? No, that's not good. We do not want to let our signal currents flow through multiple paths. So with signal referencing, very few critically located connections is what we're going to be interested in achieving. I like to make an analogy between signal grounding and safety grounding. I think in many ways they're very much the same. There are a few differences, but they tend to be more alike than they are not alike. In power distribution, we have the two conductors that carry the power current, and then we have the equipment grounding conductor that is there to reduce a voltage difference but not carry significant current under normal operating conditions. So 2 current carrying conductors that complete the power loop and a non-current carrying safety conductor. Non-current carrying under normal conditions. We already admitted that under lightning and fault conditions there may be a temporary surge of current through the safety grounding conductor. Now if you look at the signal path, the signal currents are all going to need a return path back to their source. Signal currents go out, signal currents return back. I would not want to call the signal return path ground. There's not an analogy between this conductor and ground. There's an analogy between the return path and the neutral. If you wanted to call the signal return path signal neutral, I'd be in agreement with that. You want to call it signal common, I wouldn't mind that term either. Just don't call the signal return path ground. As soon as we do that, we get to thinking that that return path has got something to do with grounding. As soon as we start thinking that way, we're going to be doomed. We're never going to recover from that situation. We're always going to have noise troubles from thereafter. It's such a simple mistake. It's what I call a kindergarten level mistake. And yet it's such a simple thing that we don't give much thought to it. We don't go back and reevaluate what is grounding, why are we grounding circuits. We just don't go back and think about that enough. Maybe this program will give you an opportunity to review those ideas and rethink them again. But I think this conductor is the signal return or signal neutral. If we decide it's a good idea to connect the internal signal circuit to the external chassis using a non-signal carrying conductor, then this could become our signal referencing or signal grounding conductor. Now later on we'll have to decide if it's a good idea to do that. Sometimes you want the internal signal referenced or connected to the external metal chassis, and sometimes that's one of the worst things you can do. And also sometimes you want the signal referenced or connected, say, at high frequency, but you don't want it connected at low frequency. So occasionally we'll use a frequency-dependent connection. Sometimes we'll put a capacitor in here and make it effective at high frequency but not effective at low frequency. When it comes to controlling ground voltage differences so that they don't cause us either safety or referencing problems, we have 2 basic choices. The ground voltage difference that we are concerned about, we can either reduce that voltage by basically trying to short it out, or we can not connect to it, avoid connecting to it. Those are 2 ways to control that voltage. That leads naturally to 2 grounding techniques. If we reduce the ground voltage difference, we're basically going to put a low resistance conductor in parallel with that voltage and attempt, by lowering the resistance, to short it out. Sometimes this is in the form of a single wire, but in some cases it's in the form of multiple grid-like array of conductors. That's why it's called a ground grid here. We could say a ground wire in some instances also. So either we short out the voltage difference, or we avoid connecting to that voltage difference. And in this manner what we do is we connect our circuitry to ground only at one point. We don't connect at multiple points. The official name for this is isolated grounding, because the equipment chassis and the grounding conductors and so forth need to be isolated from the larger ground structure so they don't inadvertently touch where they should not touch. You actually use insulated ground wires, which therefore isolates them from other surfaces, and by doing that you can control the single point at which they contact with the ground structure. So there's 2 grounding techniques. Let's review just a moment. There's 2 reasons for grounding. One is safety, one is signal referencing, and then there's 2 ways to implement grounding. If there's a ground voltage you're trying to control, you can either try to short it out by using a low resistance connection, or you can try to connect to only one side of the ground voltage difference, not connect to both sides of the ground voltage difference. Now I said shorting it out with a low resistance. Earlier we spent a lot of time talking about how impedance is the critical parameter. Impedance, which largely means inductance. Why am I now back to talking about resistance? Well, most of the ground voltage differences we are concerned about are created by power line frequency situations. We've got 60 hertz or 50 hertz power currents that inadvertently flow through the ground system. And of course there are harmonics, 3rd, 5th, 9th harmonics. And we even have variable speed drives, which have some kilohertz frequencies. But most of the dominant current in the ground structure mostly is low frequency current, something in the kilohertz range or almost down to 60 hertz. Because it's mostly low frequency, that's why we're more concerned about the resistance of the ground structure than the inductance usually. But I guess as the frequencies of currents we put in the ground system, as they get higher and higher, maybe we'll have to look at some inductive effects eventually as well. Let's look at how we can control the ground voltage difference with a resistive connection. This represents 2 points in the ground system. Maybe it's in the building, between 2 points in a building. There's resistance between those 2 points. And there's current flowing through that resistance. And the IR drop is the voltage that we are concerned about. If we can successfully lower the resistance, then we can lower the voltage and have less noise trouble as a result. And usually that's the thing we try to do. Of the two variables, the current and the resistance that produce the voltage, we usually have very little control over the current and a lot more control over the resistance. Now, if it were possible, if you had a situation where you knew there was considerable amount of, say, AC power current flowing through ground, and you had a way by rearranging the power wiring, of course, a lot of AC power current in the ground system probably means there is a problem, a mistake with the power wiring. If we had a way of reworking the power wiring to reduce most of that current in the ground system, that's certainly what we'd want to do. That could be an easy way to reduce the voltage differences. But if the current is coming from a place we have no control over or no knowledge of, then our best approach is probably to work on reducing the resistance of the ground structure. And that's what most people do. They try to lower the resistance. They have more control over that than they do the current usually. So that's one of our grounding schemes. Now, the way this may actually look in an elaborate situation, say we're putting a large amount of electronics in a room within a building. Instead of running just, quite a few individual ground wires, what we might do is run an array of grounding conductors that crisscross and probably are welded together at the joints, so we have good, durable electrical contact over a long period. We do a ground grid in this case. Now, if this grid is more than about 10 feet square, 10 feet on a side, and often it is, the larger the grid, the more likely we're going to have to tie the grid into building steel at multiple places, at least at the four corners. And the larger the grid becomes, the more often we're going to have to tie it into building steel. And this is all a matter of safety. We really don't have any choice in this. It would not make any sense safety-wise to have a metal grid 200 feet on a side tied to building steel at just one point. If you're off on one corner of the grid away from that one tie point, then between the grid and the building, there could be significant hazardous voltage present. So we'd have to tie the two together to make it an adequately safe situation. So we tend to need to multiply ground this grid. The problem that presents is the building currents have easy access to the grid. They can get onto and off the grid at multiple places. So there will be considerable current flowing through the grid, but it'll be low frequency current. That's the good part. And if the grid has sufficiently low resistance, it may be an adequately reasonable situation. Here's a situation you would not want to try, however. Say we use the ground grid approach, but we've got single-ended, low-frequency audio, low-frequency signals that are grounded to both chassis that are then tied to the grid. This wouldn't work. Even though we've got a low-resistance grid, we are still going to have several millivolts or more of low-frequency noise across the grid, and that voltage will appear right across the signal return path. In a situation like this, with a low-level, low-frequency signal, we shouldn't use the ground grid approach. We should use the single-point grounding approach in that application. Comment or two about single-point grounding. In this case, we show the two equipment chassis between which the signal flows. Maybe it's multiple signals back and forth. But say they're low-level, millivolt, low-frequency, kilohertz analog signals. We're going to tie both of those chassis to the same point on the ground structure. In that situation, we are not trying to eliminate this voltage. We're assuming that we cannot get this voltage low enough. We're going to take another approach. We're going to refuse to connect to this voltage. We're going to use a single-point grounding approach. And we're just going to avoid the voltage that is likely going to be present. Single-point grounding is what you want to use, or consider at least, if you're dealing with low-level, low-frequency type signals. It is a little bit susceptible to higher frequency noise, although if we're talking about 100 megahertz kind of noise frequencies getting into this system, I really wouldn't look to the grounding system to control the problem. A lot of people do, but I don't think that's right. I think with high frequency RF type problems, 100 megahertz type problems, there you use the metal box design, you use shielding on the cables, you try to keep the RF energy either inside the system or you try to keep it outside the system by cable shield and box design. I don't think you really want to rely primarily on some kind of a low impedance ground grid at RF frequencies. It's not going to be that. If we rely on that situation, we're going to be disappointed. So RF purposes, I don't think we rely so much on grounding. I think we rely on other situations. But audio frequency type situations, like we're talking about here, I believe grounding can help a lot to control the noise. And here we're looking at single point grounding. The symbols that we use are about as misleading, unfortunately, as the words that we use. The IEEE has a standard for electronic symbols. This symbol right here is supposed to represent a connection to an electrical ground structure, such as building steel. And of course, the primary reason we would do something like that would be for safety, electrical safety. So this symbol should be used for a grounding connection, primarily related to safety. The IEEE standard says that this symbol is to represent a connection to a non-current carrying metal chassis. Now, in most instances, maybe not every time, but most of the time when we make that connection, it's some kind of a signal grounding connection. It may have a little bit to do with safety, but it probably has more to do with signal referencing than it does safety. But even so, this is still a grounding symbol. These two symbols here do not represent connections that carry significant current. On the other hand, when we use this symbol, now we're talking about something completely different. We're talking about returning the signal current back to its source, or the power currents back to their sources. This is a signal return symbol, not a grounding symbol. So we want to be very careful how we use the symbols. We have to draw a heavy line right between here. The two symbols above are related to grounding if they're used correctly, and they represent conductors that don't carry current. And the symbol below, whether it's a solid or an open triangle, is used or should be used to represent a signal common or a signal return path. Let's talk a moment or two about ground loops. Ground loops get a lot of bad press, as if they're causing all of our noise troubles. They cause quite a few troubles, but they're not the dominant problem. But anyway, there's some trouble. What is a ground loop? I think a ground loop is a loop which contains part of its path is from the signal, and part of this path or part of this loop is in the ground structure. It's a loop, part of which is signal conductor, part of which is ground structure. To me, that's the situation you need to have to say you have a true ground loop noise problem. Now, ground loops are going to couple noise. Mostly we're concerned about into a system, I guess occasionally with it going out of the system, but how is this noise going to couple in? Well, by having multiple ties to ground, we have a good opportunity of unwanted conductive coupling. And because of the loop involved, we have a good possibility of unwanted magnetic flux coupling, mutual inductance. So those are the two problems. Ground loop noise is coupling that we don't want, most of the time conductive, occasionally magnetic. Now you could say, what about the other two? What about electric field coupling and what about electromagnetic wave coupling? Well, theoretically, they can occur with a ground loop. But practically speaking, they're not very significant. These are the two practical problems. Let's look at the classic ground loop problem. This is it right here. We have a signal running between two chassis. And I show the signal is grounded at this chassis. Now we ought to stop and ask why. Why did we do that? Why is that signal referenced to that chassis? Was that a good idea? We may decide after we see the trouble here that that wasn't such a good idea. And again, on the other end, this signal return path, the signal return path is again connected to that chassis. Why did we do that? That could have been a very serious mistake. What results now is the signal return conductor combined with the safety ground, combined with building steel, combined with the other safety ground. That forms a troublesome ground loop. That ground loop can bring noise in either conductively or through magnetic coupling. What's the typical solution for a ground loop? Well, now here's a unique situation. It's not very often that one technique can solve multiple problems. But in this case, it's true. If we open up the loop, we can eliminate both the conductively coupled problem and we can eliminate the magnetic loop problem with the same approach. That's why that's such a favorite approach. Open the loop. Now the question is where? Where can we legally open the loop? If we disconnect the safety ground, that'll eliminate the noise trouble and create a safety hazard. So it's not legal to open the loop. Most of the time it's not legal to do it with the safety ground connection. The best place to open the loop, I would say, is right here at this receiver. Why is this lead for the receiver tied to chassis? If we had used a differential receiver instead of a grounded input receiver, then this connection would not be present and we wouldn't have a ground loop to be talking about here. So I think, yes, opening the loop is a good idea. We're probably going to have to do it somehow in the signal path. Disconnect the signal from chassis on one end. And usually it's easier to do at the receiver end. Or possibly if the receiver and the driver and everything is built, then maybe we have to open the loop in the signal path. Put a transformer coupler in there if it's an analog circuit, or maybe an optocoupler if it's a digital circuit. That's a lot of trouble, but that's a way to legally open the loop without creating a safety hazard. We could try, since we're talking about common mode currents here, we could try a common mode filter. We could try safety grounding the chassis, these two chassis, not to two different points. But what about safety grounding both chassis to the same point, using single point safety ground? That would help some. There would still be a loop of some sort to deal with, however. But opening the loop in the signal path would be one of our best options here. Let's try a couple of safety-related problems. Let's say we have a metal equipment chassis that is supposed to be grounded. But because of our fear of picking up noise from building steel, we've decided maybe not to ground or connect our chassis to building steel. But because it was designed to be grounded, let's assume that in the AC power line filter, there are capacitors from line to chassis and neutral to chassis for transient suppression of common mode noise. Well, if those capacitors are present and the chassis is not grounded, you'll have 40 or 50 or 60 volts on the chassis relative to ground, just because of the capacitive divider action of those two elements. This can be a serious problem. This can be a safety hazard. Of course, there are rules about how large these capacitors can be, such that they probably are not able to conduct enough current to be a totally serious problem. But we just got to realize, if a metal chassis is intended to be grounded, very likely there will be these capacitors, common mode capacitors between line, neutral, and chassis, and we'll need to ground that chassis to reduce the common mode voltage. Now you could say, well, I've got a VCR chassis at home. It's in a metal box, but it doesn't have a ground wire connected to that chassis. Well, that's a different story. That's a chassis that's intended to be safe when not grounded. You will not find the capacitors we're talking about here connected between line and chassis and neutral and chassis. They have to use common mode filtering. If they feel a need for it, they have to do it some other way. But because those capacitors are not present, that chassis is safe if it's not grounded. It's when it was intended to be grounded that we've got to be particularly concerned. Here's another major fallacy. A lot of times we think that if we connect our equipment chassis to the noisy building with a safety ground, that we're going to pick up a lot of noise from the building. Well, if we do that indiscriminately, that's certainly true. If we connect our circuit multiple times to building ground, yes, we're going to get into a lot of trouble. But here's the situation that people will do occasionally. They will take a very critical piece of equipment, and instead of grounding it to the noisy building ground, they set up a separate earth ground that is just for use by this equipment. So you've got to watch the terms low noise ground, quiet ground, clean ground. Sometimes they mean this sort of situation here. This is a direct, serious violation of the safety code. This is not allowable. And not only is it a personnel safety hazard, it's really a safety hazard for the equipment. Imagine that we've set up an earth ground that is, say, some distance away from the building so that these two grounds are well isolated. Let's say these are a couple of 100 feet apart. Lightning hits the area here. There's going to be several thousand volts between these two ground points. And that voltage is now going to wind up inside between the power line and the chassis. And something's going to arc over and be damaged internally. So this is not a good idea. It's not a good idea from a safety point of view. It's just not a good approach. And you want to watch for this situation. This is done quite often, and it's something we need to correct. Review a couple of items. What are the two reasons for grounding? The number one reason is safety. And there you can use multiple connections in parallel with one another, and that doesn't cause the safety to be reduced. Then there's signal referencing. Signal referencing, we're going to connect the reference conductor for maybe the analog side to the reference for the digital side. That's one example. We'll look at some others later. But in signal referencing, we're going to use very few referencing connections, probably just one. What are the two grounding techniques? Use a ground grid or maybe simply a ground wire to try and short out the voltage difference that's causing us the problem. Or we use single point grounding, isolated grounding, to avoid connecting to both sides of the noise source. A key thing to remember is returning signal and power currents back to their sources. It's very important for reducing loop area, reducing picking up of stray magnetic fields and so forth. But this is not grounding. It has nothing to do with grounding. It's just good signal routing. We want to be sure and keep separate the routing of signals from the grounding of signals. Grounding conductors may carry small amounts of current. They may carry a little bit of what we might call noise currents. But grounding conductors are not to be the primary signal conductors. In fact, I would say if a grounding conductor is carrying even 5% of the signal current, I would rethink it. I would think of it now as part of the signal path and not part of the grounding system. Of course, I probably don't want it to be that way. I want it to be part of the grounding system, so I may have to do something special to make sure that I am able to get the noise currents out of the grounding system. You see, if our signal currents unfortunately have access to the grounding system, then what does that say about noise currents in the grounding system having access to our signal path? It says they have access, and we don't want that either. So if we can see a way in which our particularly low frequency signals, which remember go everywhere, if there are multiple paths, some of which involve ground, then that's not a good situation. We do not want our signal currents having access to ground, because we do not want ground currents having access to our signal path. Here's another example where isolated grounding has been used. This metal chassis has been tied to building steel at only one point. In some instances that can be good, but in this case the distance it was connected to building steel is 1,000 feet away. That's probably not safe at all. What's going to happen then is if this is the building steel here, if someone is standing out here on the building steel touching this chassis, they put the voltage difference between this point on the building and the chassis, and the chassis is tied over here. So the chassis is connected here, the person is standing here. This voltage across 1,000 feet of building steel is what is applied across this person's body. Not normally a safe situation. So if we're going to use the single point grounding, where we're going to ground one or more chassis to only a special location, we've got to make sure that the distance for that insulated grounding conductor is acceptably short. Again, I can't tell you how short it has to be. That depends on the particular circumstances. Most situations, a distance of 100 feet is, we want to be under that distance. What if you say the AC power source, though, it's 1,000 feet away? Then we're going to have to move the power source out closer to the load. One standard way to do that is to use an isolation transformer, a one-to-one transformer, to move the grounded neutral out to a point very near the load. This concludes session 4.